Chapter 6, Bending Part B, Parallel Access Theorem. Just consider we want to calculate the moment, determine the moment of inertia for a rectangle about its centroid. So that's about x prime axis. In that case, if we just develop a narrow rectangular strip with the dimension of our shape is h, height of h, and width of b. So if we just go with the same width and just by a thickness of dy prime. Mhm. In that case, our element of area it's b times dy prime. Mhm. And then ix is, if we want to develop the moment of inertia, ix prime is equal to integration of y prime, which is here, squared dA. And dA, if you just replace dA by b, dy prime. And then integrate it from minus h over 2 to a plus positive h over 2. It just sweep all the area and gives you the moment of inertia of a rectangle. So if you do so, it just gives you a numeric value of a ix prime for a rectangle is a 112 base cube height. Mhm. Let's follow the same if we want to calculate the moment of inertia for a triangular with the same dimension of h and b. Just so triangular area about its base. So just consider we can again develop our strip by the thickness of dy and just by the length of x, and x is our variation. So again, if we do know the equation of this line is provided, and if you want to do that, you can easily calculate. If you know the specification of 2 point, you can get the slope of that line and equation of the line as well. So that's a0 and h, and this one is b and 0. So with just knowing these 2 points, you can do the math and gets the equation. Then if you rearrange this equation about x, x is equal to something, then x dy dA is x dy. Then do the integration, you can have it as well. So if you move on, dA give you x dy. Mhm. As we discussed about it, if you rearrange the equation of this line a upon base of x, it gives you b minus b over h times y. And then if you just replace in dA, it just gives you the element of area, and ix is just y squared, y squared, this is y dA. And if you just replace the numeric value and solve it, it just gives you ix for a rectangle, a triangle with the same dimension of our rectangle gives us again a 12 base cube height. But it just uh, uh, make a small confusion that if I do have a book in my hand with the height of h and width of b, and I just keep it in rotation about the x-axis, it just gives me a moment of inertia of x as a, a 12 of base cube height. And again, the second uh, example just tells me if you cut it at the diagonal, and again keep it in revolution on x-axis, it gives you the same, amount of moment of inertia, and that's uh, a bit of a strange. But if you take a closer look to the problem, it just gives you the logic of when we do the mass. Yes, ix is for a rectangle is a 112 base cube height, And at the same time, for a rectangle with the same dimension, it just goes by again a 112 base cube height. But if you look at the problem statement at the same time, if you have a closer look to the problem, you can see the moment of inertia for a rectangle goes through the centroid and gives you this value, but the one for triangle goes by the base and gives you this value. And that leads us to a very interesting fact of a parallel access theorem. Let's see how that goes. Parallel access theorem, it just says if you are settled in your old apartment of x prime and y prime, and this is you. That's our dA. And if you just want to travel to a brand new apartment of x and y, so it just says your centroid, it simply moves downward to the new origin. And we do know the ix prime for the old house is just ix prime. Ix prime is the distance y prime squared, integration of y prime squared, just dA. If you just want to know what the ix for brand new house, that's just a your previous distance plus dy, which is the distance from the centroid to the new house. The old distance plus new distance, all in parentheses, then squared them, and that times dA again. That gives you the moment of inertia about x-axis. Then, if we want to know, if we just open that equation, it just gives you a ix is equal to the first term is nothing but ix prime, I moment of inertia for new house is equal to moment of inertia of the old house plus, let's go by here first. So that's dy times integration of dy squared times integration of the area. So this integration goes by area itself, gives me an area, and that's just a dy squared. Mhm. And if you remember from the a concept of moment of inertia, which I will provide you the link of the video at the end of this video, that's y prime dA. It says if you have a condition in which there is an area, mhm, and if the, the centroid of that area passes through an axis which you are making the moment of inertia. So that's something like x prime. That if you remember y prime dA, integration of y prime dA, do you remember integration of dA over area? It just gives you area. That was zero moment of an area. Y dA is just goes by Qx, and that's first moment. And this is exactly first moment of inertia. And if the moment, if the centroid of the area passes through the axis, there is no y. So if it was my area and this was centroid and this was my y. So I can go by y prime. There is a distance, then I can make the first moment of an area. If there is no y prime, uh if there is no distance between centroid and axis, y prime goes zero, integration goes zero, this goes zero. So that says ix is equal to ix prime. Moment of inertia of new house is just the old one plus a area times d squared. That's a interesting fact about the moment of inertia. Mhm. Let's make it a bit more cleaner. So, and that's how the concept is comes to play and make a a huge matter of deals in understanding the formula, so that the concept of first, zeroth, and second moment of an area, which we can have it here. Mhm. So the one more fact you need to do, it just says if you are traveling from home to any other axis. Uh-huh. So that's a positive. If you going back home from any other axis, that's a negative. So that says again, if you are going back from, if you're going out of home, you're getting something, that's a plus. And if you're coming back to home, you're losing, that's a minus. So just stick with this uh, uh, interesting concept, but an easy and interesting in your problem solving. Let's go back to our problem to see how that goes. And that's a very easy understanding of the parallel access theorem of how it goes. It works both ways. So let's see. Here we had for our rectangle, we had ix prime for centroid. Mhm, which was, we calculate that, we see that it was a 12 base cube height, and at the same time we had uh, x. Let's go by base. We get the I base for that, for a rectangle, for a triangle to be a 12. Do you remember, it is two was equal to each other, but they were for different axes. So the first one for the centroid, and the other one was for the a base. So it just parallel access theory. It just says if you want to go from any other axis to center, by center I mean centroid, mhm, you need to say if this is x prime, ix prime is ix. I'm going to home, or I'm coming back to home. I'm going home, so that's a negative, minus a d squared. Centroid of a rectangle is h over 3. So if this is h, that's h over 3, and our area. So let's see how that works. That's a 1/12. So definitely the moment of inertia for centroid would be less than that, because you're subtracting something. That's a 1/12 base, uh, 1/12 base cube height, minus what? A half of bh times h over 3 squared. And if you do the math, it gives you a ix prime is equal to this time a 136 bh squared. Likewise, and which you can see, it's far easier, smaller than the moment of inertia for a rectangle. So it says if you have a rectangle and you cut it by the diagonal, the area goes by half. The moment of inertia about the centroid of the shape, even it's not the same. It's not even a half. It's a, if you see, 136 is a 1/3 of 1/12. So that's, the area goes by half, but the moment of inertia goes by 1/3. And that's also, you can apply the same concept if you want to travel from a center to any other axis. That's a plus. And that's ix. In that terms, it's ix prime centroid. This time plus. I'm going out, it's a plus a d squared. If you do the math, it gives you a ix is 1/3 of base cube height for the corners, at the sides. For center is 1/12, for the sides is 1/3. You can easily see how it increases. It says if I want to rotate the book about the center, it gives me a less resistant than if I want to rotate it about the one end of the book. So you can easily see how your hand is getting more tired when you do the the rotation revolution about one end of the book. That's the concept of a moment of inertia in a comprehensive example. Thank you.